class 7 of post mid-semester session for the course CH425 and CH812. Okay, so we start from here today. Can you just a minute? Can you see the slides? I just projected. Should be visible.
Yes, sir. No, it's coming.
Coming, no?
Yes, sir.
Can
Visible.
you? Yeah. Okay. Okay. Yeah, we'll start from here. This size is fine, no? Okay. So, yeah. We are doing this variational principle. I think you remember we had this script E. You remember this script E?
Yes, sir.
What was the definition? I think I had used this kind of notation, maybe phi square, phi for the Gauss function, no?
Yes, sir.
Yes, sir.
Like this. This is the notation. You can put d tau anywhere, here or there. Anyway, it is the integral. So what was the assumption? Actually, we take it for granted, which I did not prove. So we have to take it for granted. We had something like the script E is greater than equal to E0. And this is our variation principle. We did not prove it, isn't it?
No, sir.
Yes. But we had taken it for granted, and I think I illustrated this with something like particle box. Remember?
Particle in a box problem. Yes,
Yes,
sir.
yes. We'll try to prove this. Actually, we're going to prove this. So the idea is as follows, that this is your Hamiltonian of the system. This is a Hamiltonian operator. Now this Hamiltonian operator corresponds to a system for which this eigenvalue equation cannot be solved exactly, isn't it? That was the idea. That was the idea. Okay. But assume that it can be solved, and this Hamiltonian would have corresponding eigenfunctions, which are like psi 0, psi 1, psi 2, like this. Okay, these are the corresponding eigenfunctions. Assume that you can solve it, and these are the corresponding eigenfunctions. And I want to prove this, that script E is greater than equal to E0. What is E0? The ground state energy, isn't it?
Yes, sir.
Lowest possible eigenstate. Energy of that lowest possible eigenstate. Now, I think you have realized that when I talk about this variation principle, I am interested in only in the ground state. Okay. So this is beautiful, this principle, but it gives you a bound which tells you that any energy you calculate using a Gauss wave function, phi is your Gauss wave function, is greater than, or at the most it is equal to the ground state energy. Okay. So let us now calculate this, whatever is here. But as you know from the postulate of quantum mechanics, what do you know? That you know that if you have a complete set, then any wave function in that Hilbert space um, can be expressed as a linear combination of uh, these eigen functions. This you know, no? This is a postulate of quantum mechanics, no?
Yes, sir. The completeness theorem.
Yeah, the completeness. Okay, so we'll make use of that. So let us do this. So let us calculate this integral first. Now, this one can be written like this, no? Just to know that you guys follow this notation. This is fine. If I write like this, is this fine?
Yes, sir.
Okay, good. So anyway, I'm not going to use this. I can use the integral thing. Anyway, doesn't matter. So this is equal to, so it is going to be something like Ci star psi I star I times H. This is a Hamiltonian operator which is Hermitian, obviously. Sorry. And you integrate this over whole space. Okay. So now I have this, no? I know that if H operates on psi I, what I get something like EI times psi I back, isn't it? Okay, so this will operate on psi I. Is this clear? This is very simple thing. Okay, this will operate on psi I. So if I do this, what I'm going to get something like, let us put it like this, Ci star psi I star, and this will give me what? Tell me.
Some EI.
EI, but then psi I is there, no?
Yes,
Don't
yes,
forget.
yes,
Don't forget. And now I can do like this. What I can do like this. What I have here is Ci star Ci. Then what else? Then I have this is fine with you? Is this fine? So what is this? This is nothing but, if I write explicitly, this will be something like C0 C0. Like this, no? One term will be like this. Is this fine? This one term is going to be like this. Of course, you have a EI. I just forgot to put EI. One term will be like this. The first term, when I equals to 0. Are you following? What will be the next term?
The E1 C0
E1
C1
C1.
star
So let us
C1.
let us take
Yes.
write this, like there is nothing called next term, but let me write this term. There is some diagonal terms, there will be some off diagonal terms, isn't it? Like this. But at the same time, you'll have a term like, what? Tell me, what are the terms, other terms you have? Tell me. Please tell me. What are the other terms you have?
The EN CN star CN.
En, Cn star Cn. What
And
else?
integral over d tau psi n
But
star.
you will also have this term, no? Say E1 C0 star C1 d tau psi 0 star psi 1. We'll have a term like this. There will be a term like this, isn't it? Why? Because what is this term? If I expand this term, what is this? This is, sorry, C0 star psi 0 plus C1 star psi 1 plus dot dot dot. No? What about this term? This term is C0 psi 0 plus C1 psi 1 plus C2 psi 2 plus dot dot dot. So now I have to multiply these two, no? Of course, you have a E sitting there, E1. So I'll have a term like this, isn't it? This is off diagonal
Yes, sir.
term. Now what
Yes, sir.
about this term? Tell me this integral. What is the value for this?
There is 1.
This is one we
One.
normalized, no?
Yes, sir.
What about this guy?
There is also 1.
It also
Yes.
one.
But what about this?
There is 0.
Yeah, because
Sir, how have we written this term?
psi
Even C
I
is
is
not
for an
star.
orthonormal set. Which term?
Sir, even C not star C1. Last one.
Which one? This one.
Yeah.
Yeah,
Orthogonal
because
sir said that you have written.
yeah, I put this here. The expression for phi. This is a phi star, no? Phi star H phi. Phi star is this. What is, if phi is this, then what is the phi star? Phi star is this. Pi star, Pi star. Okay? I just put it here
Okay.
because I'm expressing
Okay,
any
sir.
arbitrary. This is my guess function, no? This guess or trial function. That I am expressing as a linear combination of my eigen functions. Okay, so then if I write down, so there will be terms which will be 0, there will be terms which will be 1. So only terms which are 1 that will survive, no? So what I'm going to get? I'm going to get this integral is, it's very easy. What I'm going to get? What are the terms going to survive?
Only the diagonal term.
Yes, E0, C0 star, C0. What is the next term? Tell me.
E1, C1 star, C1.
Yes. Like En, Cn star, Cn. But they have an infinite number of terms, no? Because they have infinite eigenfunctions. This is how it is. Is this clear to all of you? Should be clear.
Yes, sir.
It's not very difficult, no? It's not very difficult. Okay, now I calculate the denominator. It is even easier. This is fine. What will be the terms? Tell me. This is what I have here, no? Inside. Sorry. So again, only when I equals to I, like diagonal terms will survive, no? Because if I expand this, I'm going to get something like, sorry. If I expand this, I'm going to get something like, what is the first term? C0 star C0, psi 0 star psi 0. I'll also have off diagonal terms like C0 star C1, psi 0 star psi 1. So what is going to happen to off diagonal terms? You have just done it, no? This is one diagonal term. What about this guy? This is
There is 0, 0.
0. So it is even simpler, no? What is the expression? This is equal to, actually,
C0
C0
star, C0 integral over, sir.
no.
Right, there is 1. Okay, okay. Yes,
Yes.
sir.
It's fine. Okay. Fine. Fine with it. Now what I need to do, I need to take a ratio of these two. That will give me script A, E. Now script E is what I have here. Divided by this. Okay, whatever. This is fine? Is this fine? This is very simple. I just take a ratio of this two because because scripted E is this. Now I do this. I subtract E0. E0 is the ground state energy. And if I do this, what is going to happen? What is going to happen? Let us write it down. What is going to happen? Tell me. The first term will be same as this, no? Sorry. This one. Minus. What is going to happen? Tell me.
E0 into
the whole
the
thing, no?
denominator. Yes,
Yes.
sir.
It's a long expression. I'm writing. It's not required actually. It is very easy. So, but this term and this term will cancel, no?
Yes, only the first term.
Yeah, this one and this one will cancel. So, what you are left with then? You're left with, so let me write it down like this. Now, any times if you write like C0 star C0, you can simplify this. No, this is nothing but mod of C0 square, isn't it? It's fine. You know, all of you should know this. It's fine.
Yes, sir. Yes, sir.
Yes. So what I'm going to put here, I'm going to put. I'm just using that fact. If you use, then you have E1 minus E0, and this is common. You can see. So the first term is going to be C1. What will be the next term? C2, no? C2 square, mod square. E2 minus, tell me, minus E0.
Yes, sir.
Yes, sir. All term E0.
Then what are Cn square, En minus?
E0.
What do you have in the denominator? What do you have in the denominator?
Modulus of C0 square
Yeah.
plus C1 square.
Okay, fine. It's fine. Any problem so far? If you have any problem, let me know. Any problem? How many of you are reading books? Reading book is very important, no? What do you think? It is important, reading books?
Yes, sir.
So how many of you are reading books? You should read books. Okay. So now, can you comment on this quantity on your right hand side? What is the sign of the quantity on your right hand side?
Sir, it's positive.
So can you see that?
So E1, E2, En all are greater than E0.
So this is positive, no? This is mod of something square, no? Isn't it? It's a mod of something square.
Yes, sir. Yes, sir.
This is positive. These are also positive. And what about E1 minus E0? Is also positive, isn't it? Because E1, E2, they lie above E0, isn't it? So the whole quantity is positive. So can I say that then this one is this, which basically means your scripted E is, and you have proved it. Okay? Are you convinced now that the variational calculation, whatever the case or the trial wave function I choose, I cannot get any energy which is below the ground state. Of course, it will give me energy which is above ground state. At the most, you'll get energy which is equal to the ground state energy. Is this fine?
So this will always, the
Yes.
approximate energy will be greater than or equal
Yes,
to
yes,
ground
yes,
state energy.
yes, yes, yes.
Sir, is there any system for which, sir, approximate energy will be less?
No, this is a bound. This is a bound given by variation principle. You cannot break this. No, it's a bound. It's always the case, and that is the problem now. Why it is the problem? Why it is a problem? The problem because we cannot have variation principle for the excited states. That's the problem. Anyway, we are considering only the ground state. Now we want to go back to particle box problem. We had this. What are the wave function? Remember the wave function we guessed?
Yes, sir.
What was it? X into a
A
minus
minus
x.
X.
You remember? How can you improve? Any suggestion? How can you improve? Improve. A better guess. You remember that if I do this, what is the energy I'm getting? I was getting E script. You remember that? 10.
Yes, sir.
Sorry.
Times the ground state energy.
Yeah.
1.3% error.
Something like that. Yes. Remember this is
S square upon 2ms square.
this is the one, no? I think that was the expression.
Yes, sir. Yes, sir.
Yes, sir.
But if you see the ground state energy, it is given by pi square h cross s square. So you can try one more wave function, something else. So you can try this. Try this. Now, if you can try this because it is following the same boundary condition. No? At the boundaries, this wave function vanishes. This wave function vanishes. But even with this, no improvement actually. You can check, go and check. So you get the same script. Check yourself. So one way of doing this is to take a linear combination of this and this. So I can get a phi guess. I'm calling it phi guess, which is something like this: x a minus x plus this. I take a linear combination of this, and I put usually I put a coefficient, no, c1 times this, c2 times this. So what I'm going to do, I'm going to put only one coefficient here, and I'm putting a coefficient like alpha divided by a square. That is my coefficient. Just to take care of is the coefficient. Just because it's a length square, no? So I just want to make the coefficient dimensionless alpha. So the whole coefficient is alpha divided by a square. Okay, and essentially I'm taking linear combination, no? Why you can take linear combination in quantum mechanics? Can anyone tell me? And it works? The general question. In quantum mechanics, we all the time take linear combination of wave functions. Why?
Superposition principle.
Completeness.
Yeah, superposition. But why superposition works in quantum mechanics? Why it works?
Simultaneous eigenfunctions.
The Copenhagen interpretation.
Hmm? No, actually, this is because the fundamental, the theory of quantum mechanics is a linear theory. No, it is essentially what you're doing. You're doing linear algebra. That's why you can take linear combination, isn't it? All the operators in quantum mechanics are linear operators. Essentially, you are working in linear vector space. That's why you can take a linear combination, and that works. That is also a solution to the Schrodinger equation. Anyways, so we'll do, now what I can do, I can just plot this scripted E divided by twice m a square. Okay, I plot as a function of alpha, and also I put E naught, sorry, E0. I just plot E0 by pi square h square, pi square h bar square, which is whatever, not this, but sorry, E0 by twice m square by h plus s square. So this is what actually, this is what I'm plotting, and this is equal to pi square, and this will be, so I can put one thing. So if I plot this E0 by h cross square by twice m square, the value is something like this. This is constant, no? This is your E0 divided by h cross square twice m square. What is the value? This is pi square. 9 point something. What is the value of pi square? Exact value can tell you, no, not exact, but approximate value of pi square. What is the value of pi square? 9 point what?
9.87.
9.87. Okay, so this is something like 9.87. Check yourself. Now this is plotted against alpha. When alpha is 0, what is the value of this quantity? Script E divided by whatever h cross square by twice m square. What is the value? You know this, no?
10.
Yeah, it is 10.
Yes, sir. 10.
So maybe this is hand drawn, of course. I can say this is your 10. At 0, 10. And now what you should do, you should vary alpha. That is why it is called variation. You vary alpha, this is a variational parameter, and eventually you should do this, whatever. Get the value of alpha. That minimizes this energy, no? So actually, if you do this, you will see that it is possible to do this calculation. I'm not going to do it. You'll see that you'll have some plot like this. So there'll be a value, some alpha star, whatever you want to call it, for which your energy is minimum and it is very, very close to your E0. It is lower than 10, but higher than 9.87. So you have a better energy. Is this clear? It's a better energy because you have a better guess wave function or a trial wave function. Is this clear? If you had taken only this trial wave function, what is the value of energy? Is 9.87 times whatever this quantity h cross square by twice m a square. But if I take a linear combination of this and then vary the coefficient alpha, there will be a value for alpha. There will be some value, optimum value for alpha, for which this energy is minimum, which is slightly above the the ground state energy. Okay, you can do yourself. You can try to find the value of alpha. I hope that you'll be able to do this on your own. I'm not going to do it. What you should do then, actually you should calculate whatever this E, scripted E, using this Gauss wave function. This is in one dimension, no? So try doing yourself. And what is the Hamiltonian for this? You know, it is nothing but inside the box is minus h cross square by twice m, second derivative of with respect to x. Okay, fine so far. This is the idea. So alpha is like a variation parameter. So actually you see that in quantum chemistry, many times you can guess a wave function, and that wave function will depend on some parameter, and you can vary that parameter and come up with an optimum parameter, the base parameter rather, for which your energy is minimum. The script E is minimum. Okay, and that is how you should follow. You should proceed. Is this clear to all of you? Please let me know. I hope this is clear. This is
Yes.
very simple thing. Very simple thing. There is nothing. So we just go to some real chemical problem. Helium atom. So helium atom. So what is the electronic Hamiltonian for the helium atom? Because we are interested in only the relative motion, not the translational motion of the atom as a whole. So I'll have. Can anyone tell me what are the terms we had written there? No? There are 2 electrons, no? This is for the first electron. You remember? Then for the second electron, the kinetic energy is. Ideally, I should have put the reduced mass here. No, I'm not putting reduced mass of electron because they are very close to the electronic mass. So that's why I'm putting the original mass of electron. Okay, what is the next term?
Electron nuclear attraction.
Electron nuclear attraction. So in this case, it will be E square divided with a minus sign 4 5 epsilon 0. What should I put here? You remember?
R1.
This is electron 1, this is electron 2, this is your nuclear, this is R1, this is R2, this is R1, 2. So this is R1, no? Similarly, you'll have another term like this, fine? What about,
Yes, sir.
then I'll have another term, no?
Yes, inter-electron repulsion.
Yes. And because of this, I have problem. Because of this electron repulsion, so this problem cannot be solved analytically because of this. This term is the culprit. This term. Maybe I'll take some other color. This term. It's electron repulsion. Now look carefully. If I take this and this together, what is this? What is this? Can anyone tell me what is this Hamiltonian?
Hydrogen atom.
Yeah, this is a Hamiltonian for a hydrogen atom. Now what I'm going to do now, I'm going to put a Z here. Okay, let me put it here and here first. Because yeah, that is what is Z? Z is a nuclear charge. If I put that, then also it holds, no? What is the value of Z for helium atom?
Is 2.
It's 2. So I had actually, I should have put 2 here, but I forgot, but I'm putting Z in general. So if you put Z in general, then this Hamiltonian is for anything. It could be for helium atom, could be also for lithium plus. No? So
Any 2 electron system.
Any 2 electron, yes. Make it little general, huh? I should have put 2 there. I just by mistake I did not put. So this for the Hamiltonian for the A for H atom. Similarly, I'll have another. I have something here. If I take this part and this part, this is also Hamiltonian for not H atom. This is like H-like, no? Hydrogenic. Why hydrogenic? For H, Z has to be what?
That has to be 1.
Yeah, but here I put a general Z.
It's a single electron system.
Yeah. For a hydrogen, no, it is single electron all the time, but nuclear charge could be more than 1, no? Hydrogenic. What is hydrogenic atom? Hydrogenic system are what? Tell me, give me an example, give me an example. Not hydrogen, but still 1 electron. Helium plus?
Helium plus lithium 2 plus.
Yeah, like this, yeah. It could be like hydrogen atom. Helium plus, like this. Now, this term makes my life difficult. Anyway, we have these 2 terms. Okay. Now you have 2 electrons. So in general, I can write that this is your total Hamiltonian. No, when the total Hamiltonian operates on the total wave function, capital psi, depends on how many coordinates. This capital psi. You have 2 electrons. Then how many coordinates?
6.
I don't have spin. I'm not considering spin here. How many coordinates?
6.
6. So rather writing 6, I can write R1 bar and R2 bar. This is fine. What is R1 bar?
This consists of x1, x2 and x3.
Yes. This is like the position vector for electron 1, no?
Yes, sir.
Either x1, y1, x1, y1, z1, or maybe r1, theta 1, phi 1, whatever. And if it operates on this, what I should get? I should get some energy is eigen value. This is a structure, but the problem is that it is not exactly solvable, isn't it? With the electron repulsion term. Why? Because of this term 1 over R12. You cannot solve this exactly, isn't it?
Yes, sir. We cannot decouple it.
Yes. Now consider a case, consider a situation. This is hypothetical, of course, which will never happen. Because here the problem is like that. You have 1 nucleus and then 2 electrons. So these 2 electrons repel each other and they are attracted to this nucleus. Now consider a situation where these 2 electrons do not repel each other. Of course, it will never happen in reality. Okay? They do not repel each other. So can you think of such a situation?
R12 is infinity.
Yes, only when, yes. But even with finite R12, I assume for the time being, this will never happen, this is hypothetical, that these 2 electrons do not repel each other. Okay. And then I'll have a very simple Hamiltonian, no? And for each hydrogenic Hamiltonian, I'll have a situation like this. H crosses square by twice m Laplacian 1 square minus uh, 4 pi epsilon 0 r1. This one operates on something like psi r1 bar. That gives you something like E1. It's fine. R1 bar means you have R theta phi, all three. Because your Laplacian 1 square involve, if you remember hydrogen atom problem, it involves theta phi and R, doesn't it? So similarly, you also have this equation for electron 2. Okay, you have these two electron equation. But and you remember what is this psi R1 for the ground state? Ground state, you remember what is the solution? What is this ground state? For the ground state, I am just considering the ground state. What is this expression? What is the expression for this? What is that wave function for the ground state?
Alpha R1 square into some.
No, what is the ground state for the ground state? The lowest possible state. What is psi R1? All of you know this.
1s orbital.
Yes, 1s orbital. Yes. So and if you write down the 1s orbital, you'll see that it is like this. You can go and check your notes. With Z equal to 1, you get hydrogen 1s orbital. This is for hydrogenic atom. Okay, the nuclear charge Z and 1 electron only. This is your 1s orbital, nothing else, no? But all these things I have written are in SI unit. So now you make a change, and this is very important when you take a quantum chemistry course. We make a jump from this SI unit to what is known as atomic unit. How many of you know about atomic unit? Has it been discussed earlier in this course before mid-sem?
No, sir.
Okay. So atomic unit is as follows, where the mass of electron is 1, H cross is 1, charge of electron is also 1. This quantity 4 pi epsilon 0 equal to 1. If I make this transformation, I go to this unit, atomic unit. Then what is going to happen to the Schrodinger equation? The first equation or the second equation, same thing. H cross is 1, no? M is 1, so I'll have only half sitting there. What about the next term? Z, E is 1. 4 pi epsilon 0 is 1. This will be this fine? Now, if you go and check your class notes, you'll find that what is E1? Anybody remembers the ground state of hydrogenic atom? It is not expected to remember. I can write down because this is Z square m to the power 4 by 32 pi square H cross S square epsilon square into 1 by n1 square. Okay, like n1 is the quantum number, obviously, and if you put n1 equal to 1, then you know it is this is for the n, for n1 rather. So you can calculate. N1 is a quantum number, so I'm writing it for electron 1. Similarly, I'll have electron 2. I'll put n2 there. You understand this n1, n2 are for 2 electrons. N1 for electron 1, n2 for electron 2. This expression you know. This is a Bohr expression. Or even if you solve hydrogen atom problem, the Schrodinger equation, exactly you get this. Then if I follow this, what I'm going to get? I'm going to get E1. What is E1 in atomic unit? Can anyone tell me? I just put this transform. Z is whatever is there, minus Z. M is 1, E is 1. And 32 pi square h cross square epsilon square is actually 2 times 16 pi square h cross square epsilon 0 square, which is nothing but 4 pi epsilon square whole square, isn't it? So this is what it is. This is fine with you? This is the expression
Yes.
in atomic unit. So in general, I'll have
minus 0.5 z square upon l square.
minus this is
0.5.
y 0.5. Yeah, half is 0.5. Yes, I don't want to write it like this. This is fine, no? Okay, this is how it is. So I know what is E1. I know what is E2. Now one can do this calculation and can show, this is very important, that one atomic unit, when you convert into electron volt, it is 27.2 electron volt. That can be shown. That can be shown. Okay, and then obvious, then what is the value of E1? In electron volt, it is minus,
Of atomic.
tell me,
0.5 atomic.
for hydrogen atom, then it is 1 by 2, which is minus half atomic unit, no? Which is minus 13.6 electron volt. Okay, is this clear? Okay.
Yes, sir.
Yeah, so this conversion is very important. So if I convert this, also my wave function will look something like Z is there. What about this? Root over pi a0 square. A0 is 1, no? Because the Bohr orbit is the unit of length here. It is R1 because of the 1 electron. This is fine. Similarly, for the second electron, it is okay. It is fine. Is it fine? Very simple things we are doing and not doing anything complicated. Then what happened to the Hamiltonian? Hamiltonian, the whole Hamiltonian is going to be, I told you that I did this part. So you'll have half Laplacian 1 square minus Z by R1, half Laplacian 2 square minus Z by R2 plus what is going to happen? 1 by R1, 2. Is this clear to all of you?
Yes, sir.
This is a total Hamiltonian. This is a repulsion with the repulsion term. And then I can say that my total wave function, I approximate this as a product of these two wave functions, psi R1. Of course, this is an approximation. Not exact, but approximation. Now, with this, of course, these are like your psi 1s. These are psi 1s, no? If I approximate like this, if I don't have this term, no 1 by R12, no repulsion. Okay. No electron repulsion. Only this part you have. If you have only this part, then what will be the energy in this case? If you have only this part, then you know that your H operating on psi will give you E times psi, no? and psi is the product of this, and H has this. What is going to happen?
Energy will react.
Yeah, so your energy is nothing but it is going to be your
1 plus E2.
E1 plus, actually, like what I'm saying that I don't know which notation I should use.
E1 1 plus E2 1.
No, I think you should use something like that. So this is a unperturbed. This is unperturbed, okay? For electron 2, for electron 1. Why it is unperturbed? Because this term is like a perturbation, isn't it? This electron repulsion. Without that, this is your, what is that? This is your H0. This is H0 and this is your H prime, isn't it? This is your perturbation. This is your unperturbed Hamiltonian. And H0 would have, H0 has two parts. What are these? H0 for electron 1 plus H0 for electron 2. So your expression, so energy is going to be energy 0, like unperturbed energy for electron 1 plus unperturbed energy for electron 2. And we're considering the ground state because this is the approximation. So what is this? This is 1s energy plus 1s energy. We have just done it. What is the expression? This is going to be minus, tell me.
1 atomic.
No, I'm just doing it for hydrogenic. I'm keeping the Z. Z square
Z square atomic.
by 2 plus Z square by 2. Okay? Atomic unit. Now it is Z square atomic unit. Okay, this is fine. Okay, so then what is this going to be for, I go to the next slide. For helium, what is this going to be? Notation is like, this is for the ground state. Okay, this has 2 electrons, which is minus Z square by 2. Let me write it down. Plus minus Z square by 2. So what is the Z value for helium? Is 2. This is minus 4 atomic unit. Can anyone tell me what is this in electron volt? Minus 4 times into, tell me, 27.2. What is the answer? Something like minus 108.8 electron volt. Without considering electron repulsion. We don't consider. Experimentally, what is the value? Can anyone tell me? Any idea? Actually, one can take helium atom, ionize 1 electron, and then ionize another electron, and from the ionization energy, one can calculate this ground state energy. Experimentally, this ground state energy is, any idea? Roughly.
Minus 7980.
It is like 78.6, whatever I have in my notes. Okay, it's like 78. So what is the error? We calculate the error. Like 40% error, no? Huge. 108 minus 78. What is the value? How much? 40. How much? This 80 and like 30 electron volt. 30 electron volt is like 40%. Huge. So it basically means this electron repulsion is extremely important. You cannot throw away. You cannot throw away electron repulsion. Is this clear? Is this clear? Okay. Now we go back to a perturbation calculation. Perturbation. What is the first order correction to the ground state? What is the expression? How many of you remember? First order correction to the ground state energy.
Matrix element of H1 to the ground state.
So let me write it down. It is going to be nothing but d tau 2, d tau 1. This 0 is for the ground state. You have 2 electron system, no? You don't forget. What is the perturbation?
1 over R1.
But what is psi 0, 0? You know this. So essentially, you have like this, no? If I approximate this as the product of 2 psi 1s, this is going to be what?
Psi 1 is 1 0 star.
Psi 1 is 1 star, psi 1 is 2 star, like this, no?
Yes, sir.
But these are real, no? These are real. So actually, I can just write like this. Sorry, write down. Just a minute, wait. So sometimes I have problem here. Has it gone? Yes. Hopefully it will work. Yeah. So you have psi 1 is R1 square times psi 1 is R2 square divided by R12. Now actually I don't need to put R1 bar and R2 bar for psi 1s. Why? Because you don't have theta phi dependence here. You remember, but I'm just putting in general. Is this clear? Just let me tell you. Let me ask you whether this is clear. Because this is what exactly I did. I just replaced my psi 0, 0 by what I have done here. I have yes. I have replaced this with what is this? This is psi 1s R1 psi 1s R2. Of course, because these are real orbitals, so I don't need to put star. Similarly, like this. Okay, you don't have star here. This is a typo. Same thing. Is this clear to all of you?
Yes.
Is it clear? It's a very simple thing we did. There's nothing extraordinary there because this is exactly what we did few minutes back. No, you wrote that total wave function is the product of 1 1s somewhere here. Yes, times another 1s. 1s for electron 1 times 1s for electron 2. This is exactly what you did. Now look at this expression carefully, the second one, the one I have written here down. What is this expression? What does it tell you? This one. Now you know that what is square of a wave function? What does it give you in quantum mechanics? If you take a square of a wave function,
Probability amplitude.
yes, like probability density it gives you, isn't it? So and you have like one probability density which is psi 1s square for the electron 1, then another probability density for psi 1 is 2, psi 1 is for the electron 2, and then you have an something in between, which is 1 over r12. R12 is what? The distance between this. So actually this is a representation of what is known as two spherically in case of 1s orbital. So this I1 square is spherical, no? So you have one spherical density, this one. Spherically symmetric density. And as if this is also true for electron 1 and electron 2, and they repel each other because you have 1 over r12. This is like Coulomb repulsion. So what will happen to because of this correction is going to be positive or negative? Can anyone tell me this correction?
Positive.
Because you have two electron density and they are repelling each other. The distance between these two is as r12. And this integral has a name in quantum mechanics. Anybody knows what is this called? This integral. This is representing two spherically symmetric electron density repelling each other. The repulsion. What kind of repulsion is this? What kind of repulsion?
Coulombic repulsion.
This is Coulombic repulsion. So this integral has a name. This is called Coulomb integral. How many of you knew about it? This integral is called Coulomb integral. How many of you knew about it, this Coulomb integral?
Yes, sir.
Yeah. So I just want to speed it up a little more. Actually, one can evaluate this integral, and this will be an assignment problem. Can be shown. I'm just giving you the answer. This is 5 by 8 times Z. Z is the nuclear charge. So this is the first order correction. This correction is, since this is repulsion, energy will increase. Energy will increase. So this is positive. This is positive. Now, with including this, what I'm going to get your energy for the ground state. What is the energy now? I'm writing only E for this. What was the expression earlier? It was minus Z square. Now you have to take this and add this, no? This is, you're going to be like 0, 0 plus 0, 1. What is the answer? Minus Z square, and then I have given you the answer, no, here? 5 by 8 Z or Z. For helium, Z2. Can anyone tell me what is this for helium? You have a calculator? This is minus 4 plus 5 by 8 into 2, which is minus 4 plus 5 by 4. What is that?
Minus 11 by 4.
Minus 11 by 4
Yes.
in atomic unit. And if I convert this into electron volt, can anyone tell me? This is actually minus 2.75 times, what is that? 27.2 electron volt. What is the answer? It is minus 74.8 electron volt. Error is 8%. Because you remember, this is experimental value. It's much better, isn't it?
Yes, sir.
So now much better. So now if you include this electronegative repulsion, then your energy becomes much better. So my next question would be, can we make it even better? How can you make it even better? So how to do even better? Any suggestion?
we can add a parameter to the nuclear charge.
Yes, yes. So I'm going to make use of how to do even better. I'm going to make use of what you have learned recently, variational principle. Okay. Now why? Now you have helium means you have nucleus to electron. Usually what happens, if you think is classically, electron 1 and 2, they don't like each other. So what is going to happen when the electron 1 is close to a nucleus and then you have electron 2, so what will happen, that electron 1 will screen electron 2. Similarly, electron 2 will screen electron 1. Screening. Is this clear to everyone? You know this screening, no? Where did you learn? In inorganic chemistry?
Yes, sir, in your chemistry.
What is screening? What is screening?
One electron seal the nuclear charge to the other.
Yeah. Yes. So you know that one electron will screen. So electrons will screen each other. From the nucleus. Okay. So electron will screen each other from the nucleus. So as a result, I can think that the nuclear charge failed by these electrons, the nuclear charge failed by these electrons will be what? Will be less than the actual charge, no? Z. There will be some, it will be lesser than what the electron, the actual nuclear charge is. So let us call this electron charge failed by the electron. This is called Z prime. And if I put Z prime, then my total wave function is going to be in terms of Z prime I writing. Can anyone tell me what is that? You remember that it was Z prime to the power 3 by 2. So it will be Z prime cube divided by pi e to the power Z prime R1. This is fine? In atomic unit I'm writing. And ideally one should calculate the script E and differentiate with respect to Z prime, put it 0. So Z prime is your variation parameter. So you should ideally you should try to find the value of Z prime for which the script E is minimum. Is this clear? Nothing, not very difficult. So let us calculate this one. What is going to happen? You have some, so this is your guess. This is the notation I'm using, no? Guess wave function, no? Earlier we had used perturbation theory. Now we are using variational theory with the variational parameter as the nuclear charge. The Z prime. The Z prime is nothing but your effective nuclear charge. You'll see. So now script E, what is the definition? You know the definition, no? You'll have pi square, pi star R1, R2, then the Hamiltonian, then phi d tau 1, d tau 2. Okay, you can put a bar if you want. Divided by what is there in the numerator? And we have done it many times. Can anyone tell me? Why you guys are silent? Why you guys are silent? Please answer.
Yes, sir.
Yeah. So only I could hear only 2-3 people, not more than that. They are the one all the time answering. Okay, and you know the Hamiltonian. But if I write down this Hamiltonian, this part of the Hamiltonian, half Laplacian 1 square minus, now Hamiltonian has Z. Now if I operate this Hamiltonian, for example, on this part, not eigenvalue equation, no? This is fine?
Yes, sir.
Yes, sir.
Because this is Z and this is Z prime. Okay, that is important. That is very important. Okay. But if we put Z equal to Z prime, then it will be an eigenvalue equation. That is an eigenvalue equation, no?
Yes, sir.
Now, what about this numerator? First, look at very carefully. What about this numerator? What is the value? You know, this is your phi. This is already normalized, no?
This would be 1.
Yes. So you don't need to worry about the numerator. Sorry, the denominator, not numerator. Denominator. Now, numerator is something which you should evaluate. So let us evaluate the numerator. What is the numerator? Numerator is your script E, and this is going to be given by the volume element. Then the first term is psi 1s. Now it depends on z prime. I'm writing it as z prime, a function of z prime. No, it depends on z prime parametrically. R1. Then psi 1s z prime R2. Then the Hamiltonian. What is the Hamiltonian? You don't need to see, no? Half Laplacian 1 square minus no e square, z by r.
Yes, sir. Z by R1.
Yeah. So we'll just what happened? Yes. Okay. Now z by sometimes you have a problem. So today's class can extend a little bit, 5-10 minutes more. I just want to finish whatever I want to teach today. So sometimes you have problem with this. I think if you write too much, then you have a problem. Just wait for a minute. But you know the Hamiltonian, no? You can write down the Hamiltonian in general. There will be terms, we'll be getting terms when you write down the Hamiltonian. Just wait for a minute or two. Anyone has a question can ask.
Sir, the psi term before the Hamiltonian should be there psi 1 is Z prime star and
Yeah, but I don't need to put it. Why would I put it? Because this is real, no?
that's the real. Yes, sir, fine.
Yes, I don't need
Okay,
to
sir.
put it. Some problem. I think it's too heavy. So anyone has any question can ask meanwhile. Anyone has a question from whatever being taught today in particular? Then
Sir, what is the general framework for solving the Coulomb integral?
okay, the Coulomb integral, actually the one I showed now, that can be solved analytically. Because if you go to electrostatics, if you have a course on electrostatics, there's actually two charge density interacting. So Coulomb repulsion, spherically symmetric. The problem becomes very difficult when you have theta and phi. You have no theta and phi here, no? You can integrate out for 1s orbiter. Okay, so in general, that is, you cannot solve it analytically. You have to solve it on a computer. So you have computer codes which will calculate this Coulomb integral.
So
And there is something called exchange integral, which I have not discussed. That is also calculated using computer. Yes.
So this integral is like psi square is like rho 1 and the other psi square is like rho 2.
Yes, yes, nothing else, nothing else. But you have like you have a, yeah, 1 over r. So
Yes.
you know that when one electron is far away, so you have one electron which is r1, which is at r1, the other one is at r2, and then you have r12. So when r1 is much larger than r2, then r12 you can approximate it as r1. And when r1 is much smaller than r2, then r12 you can approximate as r2, and then you can integrate. Okay, I'll just give it as an assignment problem.
Okay, sir.
Okay, so let us try to do it. No, this is for r1. Then psi1 is depends on z prime. R2. What is the Hamiltonian? Tell me. Z by R1.
Minus half del 2 square.
Okay. Minus half.
minus z by r2.
This is, I think, the Hamiltonian is, no?
Yes, sir.
Okay. This is fine. Now I'm going to do a trick. I told you that when you have Z in the Hamiltonian and Z prime in the wave function, you don't have eigenvalue equation. What I'm going to do, I'm going to add something and subtract something in the Hamiltonian. Here I'm going to add this minus Z prime by R1 and subtract the same. Here I'm adding this. This is fine? Adding and subtracting. Is this fine?
Yes, sir.
That's why I written in a different color. And now let us evaluate this integral. It looks bad, but it is not that bad, I can tell you. So let us do it. It's better I do it today because I don't want to continue this. So the first term, when I take, what I'm going to do, I'm going to take this grad 1 square and Z prime by R1. So this will give me an integral like this. Look very carefully. Very carefully look at it. I'm just taking this part minus this one operating on this. Obviously, I'll have another term. What is that? Okay, let me write down explicitly. And here I put this guy. And I'll have other terms. I'm not going to write now. I'm going to write later. But look at it this carefully. Can you simplify this integral? The first integral, look at. Can you simplify it?
The variables can be separated.
Yeah, just look at it carefully. This is a Hamiltonian. This, when operates on this, it is involving R1, no? First of all, it will operate only on this part. So this part, I can take it and put it here. Can I put it here? Psi 1 is Z prime R2.
Yes.
All of you. And then I can
Yes, sir.
integrate this I can integrate.
This will be 1.
And this will give me 1. And but when this operator, this hydrogen like operator, operates on psi 1 is R1, what I'm going to get? So essentially this
1.
integral
Minus
is,
Z prime.
let me write one more. So this is 1. So one you have is psi 1 is Z prime R1. This will operate on this. This will give me minus Z prime square by 2, I think. That is the eigenvalue. You go and check. It is minus Z1 Z prime square by 2. Remember? That is the eigenvalue. How many of you remember? Times this. This is exactly we did this, no? Because when this operates on this, it gives you E times psi. That E in atomic unit is minus Z square by 2. Remember? We had done it. But instead of Z, I have Z prime. We have done it just few minutes back. If I go back few slides back, you'll see it. I think it is here. Yeah, Z square by 2. Remember this one? Exactly, this is what I'm using. This will give me this, but this will give me this. But what about the next? Again, I can integrate this. This will be Z prime square by 2, which will take it out now. What about this integral? This integral is
This is again 1.
1. So this is, what about this integral? Same logic here. This one operates only on psi 2. So I can take this guy here, and then I take the integration of this. This will give me
This will give 1.
1. And then I'll have another integral here. So I'll have, in this case, I'll have integral like and what is the answer then? This is going to be
Minus Z prime square by 2.
okay. Now I'm done with 2 integrals. How many integrals are there? So I'm done with this part. See, this part I have taken. This part I have taken. Then okay, there are, this is side 2, huh? Typo is there. So, but I am left with few. What I am left with? Actually, I am left with terms like this. Let me write it down. I am left with terms like because other terms are like plus, and I can just combine them. I can put them together. One term will be something like Z prime minus Z that I can take outside the integral, isn't it? How do I get this term Z prime minus Z? I get it from here because this Z prime and Z, okay? This minus Z by R1 and plus Z prime by R1. From there I get this. So I have 1 over R1. The operator is 1 over R1. But you have 2 wave functions, no? Psi 1 is Z prime R1. Psi 1 is z prime r2 1 by r1 times psi 1 is z prime r1 psi 1 is z prime r2. This is fine. Is this fine? What I have done? A very simple thing. What I have taken here is this term, sorry, this term and this term. Can I simplify this integral? Can I simplify this integral?
Sir, repeat it again. I didn't get.
This is very simple actually. Whatever I have taken so much so far.
Or one term can be separated.
Yes, yes.
The z prime terms are taken.
So
Only
whatever
z-
taken so much here, the first two integral is like this. This guy, then this guy. This is I have taken, which is here,
Yes, sir. Yes, sir.
and this one. Let me check. This one I have taken here. Okay, then I have 1,
Yes,
2,
sir.
3, 4, 5. 5 terms are left. So these two terms I can combine. These two. This minus z by r1 and plus z prime by r1. I can combine these two. This one and this one. Can you see my cursor?
Okay. Yes, sir. Yes, sir. Yes, sir.
This
yes,
will
sir.
give you z prime minus z divided by r1, but r1 is
Yes,
inside
sir.
the integral. This is r1.
Yes, sir.
And then it is sandwiched between two f functions, no?
Yes, sir.
Now can I further simplify this integral? Can I further simplify this integral? Yes.
Or two terms can be separated.
Again, the operator is r1, 1 over r1. So I can actually take this guy. What is the answer? This is what? What it is? Tell me.
1 upon r.
No, this is 1.
Unity.
This is
Sorry,
1.
sir. 1, 1. Yes, sir. Yes, sir.
So basically, I'm writing it here. So I have z prime minus z integral okay, fine. Similarly, I'll have another term when I have taken this and this. Now I can take this guy and this guy. What I'm going to get here? Plus, what I'm going to get? Tell me. I'm going to get again the same term, no, similar term, not same. Z prime minus z integral d tau 1, d tau 2. I'm writing the wave function here. Psi 1 is z prime
Here
r1.
the term will be 1 upon r2.
Yes, you're right. This fine? Is this fine? Is this fine? So this integral I can do the same way, the one I did earlier. Can I do this the same way?
Yes, sir.
So let us do it. Again, it is, I just need 5 more minutes. So what will be the answer? Tell me. Can anyone tell me what is the answer? Here.
Z prime minus z.
Yes, within bracket.
Integral over d tau 2
Yes.
into psi 1s z prime r2
Yes.
into 1 upon r2
Yes.
psi 1s z prime r2.
So basically they are same. Only have dummy variable. One in one case you have r1, in other case you have r2. This
Yes, sir.
integral.
Yes, sir.
So that is very important, that whether you understand that. We're almost done. So I'll have a term like okay. And then I'm left with one more term. What is that term?
1 upon r 1 2.
Yes. What is that term if I write down? So that will have another term like integral now this integral is what? I can just rearrange this, no? Rearrange this and write it like this. This fine? What is this? Is this fine? What I have written here?
Yes, sir.
That should not be a problem because I can always shuffle between these. What is this integral? We have just learned a few minutes back.
Coulomb integral.
This is Coulomb integral, no? Are you convinced this is a Coulomb integral?
Yes, sir.
Okay. This is Coulomb integral. What is the answer? This is equal to 5 by
5
8.
by 8.
No, not z, but z prime here, no? In this case,
Yes, sir. Yes, z prime.
I go back to this. Now I have these two integral. Actually, you can combine these two integral, and I'm not going to do it. And one can show that this is equal to, if you evaluate this integral in terms of z, let me write it down. It is actually, you have z prime by z, no? That is there. And then they have the integral. Both the integrals are same. This is like 2 times z prime. So then what I have? What I have is script e. Remember what are the script e? I have to add the terms now. Minus z prime square by 2 plus minus z prime square by 2. So actually is going to be and then I have plus z prime minus z into 2z prime. And then 5 by 8 z prime. So if I now do this, you know what is to be done. What I'm going to get? I have to put 0, which basically implies this one is z prime square, no? This will give me minus 2z prime. What about this? This one will give me, tell me. Plus, you have 2z prime square, that will give you 4z prime, isn't it? Minus 2z plus 5 by 8. That is equal to 0. Can you solve z prime from here in terms of z? Or you can solve it actually. Do you want me to do it? It is not very difficult. It's 4 and this will give you 2z prime minus 2z equal to minus 5 by 8. This implies that z prime minus z is minus 5 by 16, or z prime is anyone has a calculator? What is the value of 5 by 16 approximately? I think this is the one I think.
It's 0.3125.
And what is then value of z prime? It is, this is your effective nuclear charge. If you have taken a course in inorganic chemistry, you will see this is exactly what you get, isn't it? Now this is not the whole story. The whole story is as follows. What is the value of epsilon? So not epsilon, rather script E. That you should calculate. You have to put the Z prime there, no? Z prime equal to what? 1.6875. I put it there. Okay? If you put it there, you will see that it is equal to minus Z by 5 by 16 whole square. And if you put Z equal to 2 for helium, no? What will the value of script E? 2 minus 5 by 16 whole square, whatever. If you do everything, it is in atomic unit, of course. This is going to be minus 77.45 electron volt. So even better, isn't it? Why? What are the experimental value? I think experimentally people have found this to be 78 point something. No, I had written somewhere. Where had I written? 78.6. What is the percentage of error? Is much less. So now using variational theory, where I take the nuclear charge to be my variation parameter, one can optimize this energy and get an energy very close to the experimentally observed energy. So this is one very good example, real life example, realistic example of variational principle, isn't it? Application of variation principle in chemistry, in chemical problems. So with this, I'll stop. Okay, and next class we are going to do something else. So anyone has any question, you can ask. I'll stop presenting now and I'll stop recording as well. Anyone has a question? If not, I think there is no class, no, this Friday, it is holiday.
Yes, sir.
So next class will be next Wednesday. Now you have some time to go through perturbation and variation. I'm done with perturbation and variation. I could not do degenerate state perturbation because it will take time. I could not do topics like Zeeman effect and Stark effect because I don't have time, because I want to move to chemical bonding. But we have discussed the basic perturbation theory, non-degenerate perturbation theory, and the variation theory. Okay. And I'll give you some second assignment. I'll give you after you submit the first assignment set, and there will be some question on variation and perturbation. So with that, we'll conclude today. We had a long class, but anyway, I wanted to finish this. I don't want to like keep it like for the next class. Okay, thank you. Any problem you ask on WhatsApp or email me. Don't shy. I'm not going to kill you. Huh? You can ask question. Any question you have in mind, you can ask. Please feel to ask question. Okay. I'll upload these notes and video later today. Okay. Bye.
Okay, sir. Thank you, sir.
Thank you, sir.
Bye.